Okay, so I think we should start. It's 4 o'clock. So we will have today a seminar by Hermann Nicolai. That's the last seminar of the course. Well, Hermann has been one of the very first to push the idea that E10 should play an important role in not only in supergravity, which was in a sense the original context, but more recently also to understand the structure of the spectrum of particles. And for that reason, I think it was a good idea to close the series of seminars with a seminar by Hermann, and he will talk about E10 and K of E10 and the role in various areas of physics, fundamental physics. So Hermann, as I said, I will repeat because not everyone was here. Hermann will pause once in a while for questions. So wait for appropriate times to raise the questions, and I will have to be here, the interface, since questions cannot be heard by the speaker, and I have to repeat them. Okay, thank you. So please go ahead.
Okay, thank you, Marc, for the introduction and for the invitation to Collège de France to give this lecture. Before I start, I would also like to send over my congratulations on the performance of the French team last evening. That was really impressive. I will talk about work I've been doing over the last few years with Thibaut Damour, Marc Henneaux, Axel Kleinschmidt, and more recently with Krzysztof Meissner from Warsaw University. And this is meant to be a sort of more global view of what we're really after with all these efforts. And as you see, it's also a question about searching for a new paradigm of fundamental physics. And my starting point is therefore not considerations about duality symmetries and so on in supergravity. No, why isn't this working? No, okay. But I would like to start out with this diagram. I'm sure you've all seen it. After more than 10 years of running, the LHC results have been out. And what you see here is, well, essentially exclusion limits on all kinds of proposals for beyond the standard model physics. So indeed, in these diagrams, you see no hints whatsoever of new physics. And I should say that more recently, there's been a little bit of discussion about G-2 for the muon, but that is too uncertain to really proceed on. So that's one point, but equally important, looking at this table, looking at the results, it seems like there's no obstacle towards taking the standard model up to the Planck scale, more or less as is. And this, at least a hint that this might not be totally wrong, comes from looking at the RG evolutions of the standard model couplings. Because with the measured values that were actually measured now at LHC to rather good precision, it seems like when you evolve these couplings up to the Planck scale, there are no Landau poles and no instabilities of effective potential. Well, there's a little bit of something around indicating a small instability of the scalar potential, but this is something that can be taken care of relatively easily. So the conclusion from these results is the standard model could survive more or less as is all the way to the Planck scale. And to me, this is one of the important outcomes of this LHC experiment. It doesn't indicate any need, if you just look at the experimental results, for going beyond the standard model in any drastic way. So what are we going to say in view of these results? The leading contender for unified theory is string theory. So the question is, of course, what has string theory to say about this situation after the LHC results have come out? Now, it's been known for a long time that string theory admits a very large number of vacua. So here's a nice review for this by Bert Schellekens, who was already involved early on in the early days of string theory in developing this idea. And more recently, the big number they already proposed back then has gone up to 10 to the 272,000 vacua. And it could well be more than that. In fact, it could even be infinitely many. And these come typically with gauge groups like this one, which you see here. This I just took from this paper by Taylor and Wang. Now, this is a huge set of possibilities, and it's of course, very big groups. And it seems like general constraints that people have been developing over the past few years under the name of swampland program do not substantially curtail this proliferation. And another feature here is that most of string phenomenology is predicated on the assumption of low energy supersymmetry. And most actual models you see on the market that are being discussed, they're usually some extension of the minimal supersymmetric extension of the standard model, the MSSM. There's very little on non-supersymmetric vacua. So it's not even known whether the standard model as is, by which I mean just the non-supersymmetric version of it, is contained in this set. Well, here I quote Der Spiegel, which is a German weekly magazine, which wrote a whole long article about this and about the question whether we live in a universe that shouldn't exist. Now, faced with this, of course, there are various possibilities. One is that, in fact, the vacuum that we see, the physics we see, is somewhere hidden in this huge set of vacua. And this would actually amount to a multiverse interpretation of string theory. Or it could also be that to link string theory to the real world, one has to look for completely different and better schemes. This I would find more appealing possibility. Now, there's something else which I want to show you here, which is very old. It hasn't received much attention. This goes back to the early days of N=8 supergravity. And back in the early 80s, there were several attempts to link N=8 supergravity to standard model phenomenology, all of which quickly failed, were shown to fail. And the one you see here is actually the last attempt. And it was put forward by Murray Gell-Mann in 1983. And he describes this as a last-ditch attempt to salvage the Haplon interpretation of N=8 supergravity. And he made a rather simple observation, namely N=8 supergravity has 56 spin-1/2 fermions. It has 8 gravitinos. Now you want to get rid of these gravitinos, you make them massive. That means you have to absorb, out of the 56, you have to absorb 8 Goldstinos, which leaves you with 48 spin-1/2 fermions, which is exactly the right number in 3 generations, including right-handed neutrinos or left-handed antineutrinos. And then he went even further and made the following observation. He said that, well, the gauge theory has a gauge group SO8 that contains SU3 cross U1. Now, your first idea might be that this is SU3 color times U1 electromagnetism, which is the unbroken symmetry down to the lowest energies, but that doesn't work. this is something he had already considered before. But then he had this very strange idea of identifying the supergravity SU3 with the diagonal subgroup of SU3 color and the hypothetical family symmetry SU3. And this is what you see here. And he said we should identify this SU3 of supergravity with the diagonal subgroup of SU3 color and SU3 family. And then this is what you get. And this is exactly what you also get from N=8 supergravity. As for the charges, what you see in the left column, this is actually what you get from supergravity, also doesn't fit. But here I've written the actual electric charges of the various particles. And then Hermann noticed that you could fix this mismatch by introducing a spurion charge equal to 1/6. And it has to alternate in a certain way that's associated with the assignments of the family group. And we were, of course, excited at the time, and we were even more excited when we realized with Nick Warner back in 1985 that this scheme is actually realized at the SU3 cross V1 stationary point of a gauged N=8 supergravity. So we were sort of hyper excited for a couple of days and tried to fix this, but we just could not get this to work. So while I keep talking about this because I find it kind of tantalizing, but the reaction of most people would be, well, it's nice numerology, but it really shows that in the end, it just doesn't work. And therefore we have to discard N=8 supergravity in our attempt to unify the fundamental interactions. I want to take a slightly different point of view on this, as you will see in the lecture as it evolves. I don't quarrel with the fact that N=8 supergravity doesn't give you the right thing, but I would like to take this as a hint of something else, whatever it is, that comes beyond supergravity. And here you have some indication, experimental indication, if you like, that something like this is needed beyond N=8 supergravity. Just like when it comes to UV finiteness of the theory, there's evidence that you may have to go all the way to string theory in order to get a finite theory of quantum gravity. So in this talk, I want to sketch some ideas in this direction, but this is by far not a finalized proposal because you will see that the gaps in our knowledge are still too big. But I simply want to point out and somehow explain why I think this seems to indicate that the way the standard model gets linked to a Planck scale unified theory of quantum gravity may work in ways completely different from currently popular ideas. And this is the idea about, or this point about paradigm, because the current paradigm, and that's also completely incorporated into string theories, you just make symmetries bigger. Say if you go to GOTS, you introduce supersymmetry, and thereby you enlarge the number of particles enormously in some cases, and also the number of couplings. And what I want to emphasize is that this may not be the right way to approach the problem. Now, this is not about, discarding notions of symmetry, but it's rather, the idea is rather, as you will see, that yes, we must go to bigger symmetries, but then we must somehow go beyond the ideas that have been used so far to implement symmetry in fundamental physics and unification. So this proposal makes use of several ingredients, namely a BKL type analysis of cosmological singularities. There's something called the E10 K10 sigma model, which is an attempt to actually formulate M theory rather than drawing pictures and big blobs with cusps at the end, but actually formulate a mathematical model of M theory with emergent space-time and matter degrees of freedom. So in some sense, analyzing the fermionic sector, I want to go beyond n equals 8 supergravity, but in some sense want to stay close to it. So the main goal is to find some way to link all these beautiful mathematics in some way to the real world. So maybe this is a good point to stop if there are already some questions at this point. Marc? Okay, good. So let's continue. So as I said, BKL is part of the essential piece of the picture. And what you see here is a space-time diagram of a cosmological space-time, which is relevant for the BKL analysis, but it's also relevant for inflationary cosmology, as you probably know. So what you see here is cosmological space-time, world lines of stationary observers. And then there's this so-called horizon problem, which means that as you approach the initial singularity, there will be causal decoupling between the spatial points. And you may notice that I've already here marked a region, which is the Planck regime, which is probably not covered by the classical description, because we all expect that when you get into the Planck regime, then some other theory has to take over. And of course, this effort is, well, it's in part devoted to understanding what this theory might be. So according to BKL, you have this decoupling of spatial points, which can be formalized into the statement that spatial gradients can be neglected in comparison to time derivatives as you approach the hypersurface t equals 0. Now, the way I want to interpret this is by saying that what this indicates that what you have at the singularity is effectively a reduction to one-dimensional system, or rather to continuous superpositions of such one-dimensional systems. This idea is not as outlandish as it may seem, that there's some one-dimensionalness at the singularity, because if one thinks about cosmological solutions of Einstein's equations, you can think of this as a one-dimensional motion in some dynamical system, namely a one-dimensional motion of a point particle that moves in the moduli space, not ordinary space-time, but moduli space of d geometries. So that is, each point in this moduli space describes a whole spatial geometry. And this moduli space is simply a space of Riemann metrics, spatial metrics divided by spatial diffeomorphisms. This is what underlies, this analysis is something that underlies a canonical quantization approaches to quantum gravity, because they would simply say that we take this moduli space or configuration space, and then we simply quantize on that space, just like Schrödinger equation quantizes the motion of a classical point particle. And this is what leads to the so-called Wheeler-DeWitt equation, with a wave function or wave functional that lives on this moduli space. Now we're interested in unification of space-time, matter, and everything. One way to say this is that M should incorporate matter degrees of freedom in a natural manner. Not simply like the canonical quantizers do, they simply quantize Einstein gravity, and once they've solved that problem or think they have to solve the problem, then they simply append matter as some kind of accessory that can be chosen at your convenience. So the question is, can we understand this moduli space and quote unquote simplify in a very advanced sense by means of embedding into some other space that, and the idea is it's a group theoretical coset space of the type that we encounter in supergravity, namely some group divided by its maximal compact subgroup. And the main conjecture is that this group is E10 and the maximal compact subgroup is something I will get to. You notice that this, in some sense, fits with the original conjecture of Bernard Julia back in 1982, that there should, E10 is the symmetry that should appear in the dimensional reduction to one dimension. But of course, it's not quite the same, because if you simply take 11-dimensional supergravity and reduce it to one dimension, you get a very simple mechanical system. And you will not only see a tiny part of this severely mutilated part of the E10 symmetry. So let's take a closer look at the Hamiltonian constraint. So here, this is what you find in every textbook on gravity, canonical gravity, and quantum gravity. So the Hamiltonian constraint has a kinetic piece where the capital pi's are the momenta canonically conjugate to the metric, to the spatial components of the metric, written here. And then there's this prefactor, which is the famous de Witt metric. And already at this point, I would emphasize that this metric, the de Witt metric, is famously indefinite. So when you reduce it appropriately, it's like a Klein-Gordon operator, and it's not like an elliptic Laplacian operator. And then there's a potential contribution, there may be matter contributions, and so on. So this is very complicated, but there's a definite simplification that takes place in the BKL limit. Namely, this is seen by reducing to one spatial point and restricting the spatial metric to diagonal form like this. And then you rewrite this Hamiltonian, and then the kinetic term simplifies with a metric, GMN, that follows out of this de Witt metric by appropriate restrictions. And then all the rest you lump into an effective potential, and you can think of it like it's being obtained, or that it is obtained by quote unquote integrating out whatever else is here on the right hand side. Now this is still an extremely complicated expression, but there's a radical simplification as you approach the singularity, because it can be shown that these potential is a sum of Toda-like potentials. And in the near singularity limit, these Toda potentials become infinitely sharp. So in fact, you now end up with at the singularity, very simple potential, which simply consists of a superposition of walls of certain linear forms, WA, or rather the leading ones. So these are still the betas, so it's linear in the betas, and then you have various wall forms, and they depend on whatever appears here on the right-hand side. They constrain the motion in such a way that you have can describe the system in terms of a billiard system, where this point particle that moves in this beta space just bounces around in a kind of wedge in this beta space. Now comes the important step, because now I want to show you how this connects to the groups, and particularly to the groups that Marc and Axel were talking about. And I assume that Marc has told you about this, and also last week I heard about it from Axel. And the steps are as follows. You identify the space of diagonal degrees of freedom, the betas, with the Cartan subalgebra of a certain Lie algebra. And furthermore, you identify the de Witt metric restricted to this beta space with the Cartan Killing metric of this algebra. And again, the important feature is that this Cartan Killing metric is indefinite, and the indefinite is inherited from the de Witt metric. And then it turns out, as was shown in a beautiful letter by Marc and Thibault, that the leading wall forms can be associated with the simple roots of some indefinite Kac-Moody algebra. In this way, you simply take these wall forms and you contract them with the de Witt metric, and then you just end up with this Cartan matrix. And there are many examples where this appears. For example, Einstein gravity in 4 dimensions leads to something called AE3. Some also call it the Feingold-Fraenkel algebra. And for the maximal theory, you get E10. And then there's a nice mathematical characterization of, for example, the BKL chaos in terms of properties of this indefinite Kac-Moody algebra. And one other thing, because we're now getting into E10, one surprising property, perhaps, that has no analog in finite dimensional Lie algebra theory, is that E10 is the maximal rank such algebra, which goes with maximally extended supergravity. And this algebra contains all simply laced hyperbolic Kac-Moody algebras. So what is E10? So here I can be quick because Axel already explained it to you. It's Lie algebra group associated with a certain Dynkin diagram, which has this form. And given this Dynkin diagram, there's a systematic procedure. It's called Chevalier presentation, where it shows you how the algebra is built from basic building blocks, and SL2 associated with each node, and then you simply write down a few defining relations. They're written here. And then E10 is the free Lie algebra that's generated by these SL2s, by commuting them in all possible ways, modulo the Jacobi identity. But the difficult part is now you also have to divide out the cell relations, and that's what makes the problem almost unsolvable. And the important feature is that the indefiniteness of the Lie algebra implies what's called exponential growth. So that means if you stop here, it's E8, finite dimensional. If it stops here, it's affine, it's infinite dimensional, but still manageably infinite dimensional. But once you add this extra node, it becomes unmanageable, at least until now. Well, E10 contains all simply laced hyperbolic Kac-Moody algebras, but it also contains many of the duality symmetries that we have encountered in studies of M theory. So here's one way to see this. This is again something that was shown by Axel. Simply, if you analyze the algebra by restricting to a subalgebra obtained by deleting one node from the Dynkin diagram, then you can get different subalgebras, and they're given here. And then they are clearly associated with these maximally supersymmetric supergravities, and also n=8 supergravity. So it looks like it provides a good framework for unifying duality symmetries, the dualities that have been encountered in supergravity and superstring theory. So where are we now with this? Well, there are tantalizing hints, but also extremely difficult questions. So one thing you can do, has been shown the past few years, that one recovers all the bosonic multiplets dynamics of maximal supergravities by appropriately slicing E10, which is really like what you want for M theory, depending on how you look at it. Out comes one of these cusps of the M theory blob that's usually shown in popular string talks. However, and this is where the difficulties really show up. First of all, that even after 50 years, there's no concrete realization of the Kac-Moody algebra. That's mainly due to the exponential growth. We've been trying to exhibit something like emergence of space-time, but this is far from resolved. We just have the first steps, but it remains a huge challenge to really work out how this works. In particular, it means understanding all these higher level representations that you get when you decompose E10. You would have no idea what their physical significance is. And finally, of course, that's as a far goal, very far in the future, how to embed and UV complete standard model. So these are difficult questions. They will not be resolved by the next string conference, or I guess not even a string conference in 10 years, although this would be very nice. So we've now moved, we'll now move to something else. Just, we're trying to make progress wherever we see an opportunity. And this now concerns the incorporation of fermions, which I think, and I will try to convince you that this is really one key thing to understand. It may actually also understand much better what E10 is all about. Now, important here, it's fermions are not simply described by some super extension of E10 with a simple, well, sorry. For the simple reason, first of all, there is no super extension. Secondly, we know from supergravity that the fermions are described by the maximal subgroup of the global duality group, as evidenced by two examples here, N=8 supergravity in 4 dimensions and in maximal supergravity in 3 dimensions. This is where these are double-valued representations of the fermions, and they're definitely not liftable to n representations. This is important because you might say, well, if you understand E10, just take some E10 representation, decompose it under this subgroup, and then you have a representation. Yes, that's true. But we, of course, those are not the ones that we're interested in. We're interested in fermionic representations, double-valued ones, and those you cannot obtain by decomposing En representations. And all of this we expect to be true, remain true for KE10. So what is KE10? Now, this is essentially a repeat of what I said about E10. Again, you have a sort of presentation for this, which is not very different from the Chevalier-Serre presentation. And this definition is entirely analogous to the one that allows you to pass from SLN, say, to its maximal compact subgroup SON. Namely, you look at a certain fixed point algebra where omega is some involution, meaning it squares to 1. The maximal compact subgroup is simply defined to be the fixed point algebra with regard to the Chevalier involution, which you see here. It's very simple. And the invariance property, of course, of this involution is very important because this is what allows you to extend the involution to all elements of the algebra, because they can all be written as multiple commutators. So you simply have to work your way backwards until you just get the omega of the fundamental generators. So if you substitute the Chevalier-Serre basis, like here, so this is the one element combination that's invariant under omega, you can deduce from the Chevalier-Serre presentation, you can also deduce these relations, which I already saw in Axel's lecture. So they look very similar to the Chevalier-Serre presentation, except that this is now inhomogeneous. And this has to do with the fact that you now get cross commutators between E's and F's and give H's, and so you eliminate some. And then in simple cases, if you have just the E10 Dinkin diagram with at most one node between, as one link between two nodes, then this is the relations that you have to solve. It looks fairly simple. And actually, this was already considered by Berman back in 1989, who also proved some theorems. And it simply means that once you find realization of these Berman relations or Berman-Serre relations, then you have a representation. So this involutory subalgebra is, well, before I said it's like E minus F. And in terms of, if you take the generators of E10, label them by their roots and by their multiplicities, then basically the generators of K10 are made up of the antisymmetric combinations. that doesn't look like a big deal for finite dimensional exceptional groups. It will just give some other group in the list of in the classification of finite dimensional algebras. But when you go infinite dimensional, this is radically different. It's a very strange beast because, first of all, it is not a Kac-Moody algebra. And one way to see this is that it does not admit a triangular decomposition, which is a basic feature of standard Kac-Moody. It has finite dimensional unfaithful representations. Again, something that you don't see for ordinary Kac-Moody algebras. And because it has such finite dimensional unfaithful representations, KE10 is not simple. It's non-simple in a very complicated way. And here already, let me say the not simple means it has non-trivial ideals. And the way this is done, you take any unfaithful representation, and then you look at the generators in KE10, which annihilate all vectors of the representation, and they form an ideal, as you can easily show. Now, for the known examples, which I'm going to discuss, as a finite these ideals have finite codimension. And that's another thing that is different from the finite dimensional case, that this orthogonal complement is not a subalgebra. This is again related to certain subtleties. Last Wednesday, we heard about subalgebras of loop algebras where you fix one point. And then you see when you want to do the orthogonal complement, you have to do like a delta function, and delta functions cannot be multiplied. And this is something that you can actually verify, certainly for K of E9, very explicitly, that this thing is spanned by non-convergent formal sums. So it's like, you know, sum 1, 1, 1, 1. Okay, so that means that it's difficult to get to these representations. Maybe there are questions at this point. Yes. Okay. So let me keep going. So this not being a Kac-Moody algebra, there are no tools for constructing representations, like highest and lowest weight representations. So this was essentially done by trial and error. And it turned out this is obtained simply by taking the fermions of maximal supergravity, namely what fermions are there? Well, there's the SUSY parameter, epsilon, the 32 component spinor. And there's the Gravitino, which is a vector spinor in 11 dimensions. And we will mostly always adopt the Coulomb gauge. So the psi 0 is not 0, but some linear combination of the other components of the Gravitino. And then this is, of course, just the SO10 rotation. There's nothing unusual about it. But you can extend it by certain operations that you simply read off from the supersymmetry transformation rules. Of course, it's not completely obvious how to do this, and it took us a while to figure this out. But anyway, for the spin 3/2, you get this. And one way to check that it's a true representation is you just check the Berman-Serre relations. Now here it's kind of easy. This is easily done for the gamma matrices. Here it's a little more work. Now I would like to emphasize that these are really double-valued representations, because one can check that if you take a real root and rotate the fermion by 2 pi, you will get a factor of -1, as you would expect for a fermion. So these fermions can be consistently coupled to the bosonic model that was developed already some time ago. And more elegantly, with appropriate truncations and all the assumptions that also went into the bosonic analysis, it turns out that the 11-dimensional Varita-Schwinger equation can be recast in a different form, namely like a Dirac equation, but with a connection that belongs to KE10. So it's like a KE10 covariant Dirac equation, or rather the beginning, I should say. You know, all of this only goes up to a certain level and then it sort of diverges. Well, Axel and I spent some time worrying about, you know, it's nice to have these examples from supergravity, but is that it, or are there other examples? And as I said, they're difficult to find, but with some guesswork, we found two more, which we called spin 5/2 and spin 7/2. Of course, has nothing to do with real spin 5/2 and real spin 7/2. It's just a name, and maybe not even the best name, but anyway. And I just show you this. I will not explain it in any detail, but this links up to Axel's lecture, and this is something he did not show. He only showed 5/2. I just showed you the most complicated example we have. There's a certain expression, and when you substitute the simple roots of E10, you can check that these expressions, if you substitute the simple roots, do satisfy the Berman-Serre relations. So they provide a non-trivial representation, which is already much, much bigger than the Gravitino. It has some 7,000 something components. So the conjecture is that there exists an infinite tower of ever-increasing finite-dimensional fermionic representations that capture more and more of K10 while remaining infinitely degenerate. So this, for example, here already allows you to probe some of the imaginary root spaces. This is where the complications lie with these indefinite Kac-Moody algebras. So you have a faithful representation on certain roots, not very many, but imaginary roots, meaning roots that square to negative numbers. There's also something about the associated quotients, another thing that was mentioned in Axel's lecture. And we think that what we found here is the beginnings of a vast generalization of the so-called generalized holonomy groups. There's been a lot of work on generalized holonomies, where you take the right-hand side of the Gravitino variation and you combine the spin connection with whatever flux is and try to reinterpret this as some kind of connection, and then you get a certain finite dimensional group. But as Axel said, there are problems with this because these people would not know how to generalize that action to the Gravitino, whereas here this is completely different. We say that the real holonomy group is K of E10, okay, of E9, if a little more modest. And what we see on these unfaithful representations is a mere shadow of this huge, well, asymmetry group, if you like, or holonomy group. So it's a little bit like Plato, you know, with Plato, people sit in the caves, they see some shadows on the wall, but they have no way to access what's really there outside of the cave. So they simply go by the shadows they see. And what I'm saying here is that these holonomy groups that have been studied in the literature so far, they're just like mere shadows of the real thing. And we're like the caveman sitting there and staring at those shadows. So here we are. These are the major challenges ahead, just as difficult as for E10. First of all, namely understand E10 via this hypothetical infinite tower of ever-increasing unfaithful representations. We have recently made some progress on this, at least for K9, which is much easier. In this paper, we're able to show that actually we can demonstrate the existence of an infinite number, infinite towers of such unfaithful representations. In terms of, and in fact, we even can provide a raison d'être for their existence. This is done by mapping the KE9 to a sort of parabolic structure. As I said, these associated quotient groups capture more and more, and you see here the ones for the representations that we found. You see this already quite big. And another strange feature is, although you're dealing with a compact group, actually this quotient group is non-compact. That's a strange fact. So you see this, if you could understand this better, there was also help with E10, because once you know KE10, you also know E10, a lot of about it. And the idea is sort of keep exhaust the algebra ever increasing bigger and bigger and bigger chunks that capture more and more of this infinite structure while remaining infinitely degenerate at each stage. So you will never be able to catch everything. And no matter how far you go, there's still an infinite tower of root spaces that you cannot faithfully capture. But you can push, if this works, you would be able to push this as far as you like. And I think this is also important for the physics, because it's probably needed to see how K10 unfolds in the physics context to give rise to emergent space-time fermions. And once you understand that, maybe you will also be able to understand how space-time emerges on the bosonic side. Again, problem for the next 20 string conferences to worry about. Well, I'm not sure whether they worry about this at all at the moment, but I think this is the thing to look at. So, you know, as I said, we try to keep doing the things that we can do. So let's now go back to this, because this, I think, is interesting physics aspect. I told you about this strange coincidence that Hermann exposed between standard model fermions and N=8 supergravity fermions. And let me repeat, there's this funny mismatch here. And, you know, in view of all the efforts that we've gone through with this, we're now convinced that there's just no way to fix this within N=8 supergravity, meaning to fix the Q and also to somehow undo this descent to the diagonal subgroup of family SU3 and SU3 color. So it's clear from that already that, you know, N=8 is not enough to match supergravity with the fermions. So now here comes the leap of faith, the way out that sort of is hinted at by all these considerations. We would like to interpret the fermionic degrees of freedom of N=8, the N=8 supermultiplet at a given spatial point. That's a strong restriction, as a special representation of K10. We no longer think of it as part of a supermultiplet, but we would like to think of it as a fermionic representation of this peculiar infinite dimensional group. So more specifically, the Rita-Schwinger representation, that's what we're looking at, that contains 8 gravitinos and 56 spin-1/2 fermions at one spatial point. And as I said, kinematically, it's still true, this counting, if you absorb 8 Goldstinos into the gravitinos, and then you end up with 48 spin-1/2 fermions, corresponding to the 3 generations of 16 quarks and leptons. Let me emphasize again, this is mere kinematics. We have no idea how this could be dynamically realized. Nevertheless, you get an interesting prediction from this, which is falsifiable, namely that besides the 48 quarks, including right-handed neutrinos, the only other particles that this model, fermionic particles that this model predicts, of this scheme, are the 8 massive gravitinos, which accompany the 48 spin-1/2 fermions. So, you know, we're easily done in if in the next 10 years somebody discovers a new, truly fundamental spin-1/2 particle, then that's it, we're cooked. So I said it's cannot be cured within N=8 supergravity, but well, I looked at this and I thought for many years, I thought, well, that's it, you know, there's nothing you can do about it. But after, 2015 or so, when the LHC results started coming out and more results came out, and nothing turned up, except standard model. Krzysztof Meissner and I sort of went back and asked ourselves, well, you know, what would it take to actually correct for this mismatch? Let's just start with electrical charges. That's the easier part. Let's just try to see what would it take to correct this, how to deform the U1 action that such a way that it gives the correct, has the correct action on the quarks and leptons. And amazingly, there's a sort of quite simple extension of, well, of the R symmetry of n equals 8 that does this. And so here, if you think about this SO8 generator, which is just imaginary unit in some sense, certainly for the SU3 cross U1 subgroup that we have studied in connection with gauge supergravity, the only thing you have to add is this funny triple product. So this is the usual co-product of SO8 to act on a threefold antisymmetric representation. So here are the fermions. So the only thing you have to add is this T wedge T wedge T. This is clearly not in SO8 or SU8. So that proves again that we're no longer within n equals 8 supergravity. So that's the first part. So what I want to show you now that it is actually in KE10. And furthermore, of course, we also need to extend the action of this Kalman spurion shift to the gravitinos. So here's the argument why this does belong to KE10. This was shown in a paper with Axel some 5 years ago. Maybe I shouldn't go in too much detail here, but we've done, you have to go back to the original Kremer-Gilliard analysis of how to get the n equals 8 fermions from 11 dimensions. There are certain redefinitions, which you see here. Many indices, I won't explain what they are because that's not really so. This would be a separate lecture, really. Anyway, one has to rewrite this in a little bit using these funny Damour-Hillman fermions, where you take the gravitinos and multiply them by a gamma matrix without summing over the spatial indices. So that breaks SO10 covariance. This is something Axel already showed you a week ago. So then you have these funny objects, and turns out that there's a very simple action of this thing on these, in this Damour-Hillman basis. And this actually provides a realization on all fermions, including the gravitinos. So that's one of the things we wanted to do. Now, how do you show that it's in KE10? For this, we need this explicit formula of the action of a KE10 generator on this fermion in this funny basis. And this, remarkably, this is a formula that works for all real roots of E10, of which there are infinitely many. So, so if it was just the gamma matrix, it was very simple because there are only finite number of them. But here you have a rather large choice, and then you can put it on a computer and check whether linear combinations that give you exactly what you want. And this is something you can do. And the important thing here is that in order, what I'm saying is, in order to achieve this match, I cannot stay within finite dimensional R symmetries. It just doesn't work. I have to go all the way to infinite dimensions. In some sense, we haven't really written a proof of this, but it's obvious in this numerical construction that you have to go to very high height E10 roots in order to make this work. And you cannot provide this shift if you simply stay within E8, E7, or even K of E9. It's not enough. So this indicates, from my point of view, that actually in order to match standard model quantum numbers with whatever the unified symmetry is, you have to go all the way to infinite dimensional groups. I should also mention that once we have this, we can generalize this to the full set of quantum numbers of the standard model, because this Q group which acts here is sufficiently large. this is at this point mere kinematics, so I cannot tell you why the theory should do this or what mechanism leads to this breaking. But there's one interesting little aspect here, which is the following, namely, if you look at this, Gell-Mann assumed an SU3 family. And if you look at it, you realize it cannot commute with SU2 weak, which is, this is because the U and the D, which form the SU2 weak doublet, they get assigned to different representations of the family SU3. You know, we try to do it otherwise, but this seems to be the only way to get this to work. So it means, this is interesting because in the old days, in times of gut theories, people tried to include family symmetries, making the groups even bigger. It didn't work in the end, but an assumption that always went into this was the family group commutes with the standard model group. And what we see here is that life is not so simple, whatever this means. So the big open questions for the next couple of years, or maybe decades, how does K10 unfold to give rise to spatial dependence that would really allow us to claim that this is really the standard model gauge group with bosonic, the vector bosons and all, and what have you. And other questions, of course, even if it's kinematically possible, how could you break this infinite dimensional symmetry to a gauge symmetry? So it's still infinite dimensional, but what would sort of bring it down to this? Difficult questions. And this is why, again, we move in some direction where we can think that we can say something. So maybe I should stop here for questions. And more questions than answers, let me emphasize again.
Okay, so the question is, you mentioned that this, what needs to be probed. So how could that be probed?
Well, I'm getting
C or and which energy scale?
I will go on. I mean, here the statement is simply that we can get this to agree with a standard model spectrum of spin 1/2 fermions. Okay, that's not much to say. I mean, it is somewhat remarkable, at least in my opinion, but that's it for the moment. You know, we've just found agreement with something we see, and if they find something new, then we can say, well, sorry, then we have to give up. Now I'm getting more to physics. This is work that
maybe I have another question then.
Yeah.
Is there, so you talked about K of E10, and you said that K of E9 would not accommodate some of this.
Yes.
Okay, but would K of E11 work, or is there anything special with respect, I mean, of K of E10 with respect to K of E11, or K of E10 is a more economic one? Or
K of E10, you mean whether KE11?
KE11, yeah, sorry.
The problem here is that I don't know what KE11 says. I mean, here the KE11, you get this quotient group SL32 instead of
Yes.
SO32. This much I know. You can probably also define the representation corresponding to the Gravitino. But from the point of view at best, I mean, because E10 is contained in E11, KE10 is contained in KE11. Yes. So maybe you can make it fit. But whether there's a mismatch here with something else, I cannot say. Because one thing that you learned from Axel's lecture, or at least one of the more recent papers he has written with, what is Guillaume and Ergin, I think, on E11, where this is sort of the point of view that I simply rewrite 11-dimensional supergravity in terms of this funny symmetry by introducing many new fields, infinitely many of them. My point of view here is that actually we're looking for something that's not simply 11-dimensional supergravity, because as I said, the compactification that leads to this SU3 cross U1 vacuum has the wrong quantum numbers. And there's no way to fix this within supergravity. So it seems clear to me that, you know, there must be something else, whatever it is. Also something else that has different dynamics. Okay, so
maybe one more question. So you are talking about this, I mean, the question of emergence of space and more derivatives. Now you have already a few ideals. Can you say that the bigger ideals is obtained from the previous one by incorporate first order derivative and then maybe second order derivatives? And is this what you hope? And are there signs for that?
Well, if there are signs, they're not very strong, because this question was already posed to Axel last week. And the thing is that what we call 5/2, it's not really 5/2 in spin 5/2 in the standard sense. It has the 5/2 representations as a sort of anti-symmetric tensor spinner, and you might try to identify this with the Rarita-Schwinger field strength, and then there's something else. But of course, you would also like to have the Rarita-Schwinger field strength with any number of spatial gradients, and that would be a very specific representation. And you would need to find more general representations that actually have something like this. And at least with the representations that we have so far, this is something we don't see. But of course, there's not much more I can say, because until we have really a more representative class of representations, then one can address this question. But at the moment, I'd say this is still a hope.
Okay, thank you.
Okay, let me now getting even closer to physics, because I was asked, and there's of course obvious questions. I mean, is there anything else you can maybe try to check to validate this ansatz? And this part of the work has been done with Christoph Meister, and that's also a little more recent, because so far the focus was on these spin 1/2 fermions. But of course, the theory also predicts then these 8 massive gravitinos. And the first thing is you ask yourself, what kind of representation then do they transform in? And it turns out this is what you get. And the funny thing is you get fractionally charged gravitinos, and these assignments include, and this is important, this Kalman shift. Otherwise you get 1/6 or 5/6 or whatever. But here you get exactly the kind of charges that you see in QCD, the quarks. This is obviously completely different from the gravitinos that you've heard about from N=1 models, which are uncharged under standard model symmetries. They're sterile, have only very weak interactions, and the only question is, what is their mass? And then, you know, they can serve as dark matter candidates, or maybe LSBs, or maybe they're much more massive, you know, but they're very hard to detect because they suffer only, they're sterile with respect to standard model interactions. This is completely different here, because, I mean, once you have a strong, it's like Gluino, you know, once it's there, we will see it. So if these things, you know, were so easily accessible, we should have seen them. But they can, of course, escape this detection if their mass is extremely high, and we hypothesize that it's close to the Planck scale. And furthermore, their cosmological abundance extremely low. Now, one nice feature of this is that these things are, you can, of course, try to make them team up with quarks and leptons and do color singlets, but you will always end up with fractional charges, and there's no final state in the standard model that has such charges, and therefore they just cannot decay. They're stable. They would be stable, assuming they exist, and therefore they're, in principle, they're dark matter candidates. But they have a very different type from the ones that have been looked at so far, because I mean, either it's something like axions with masses of 10 to the minus 8 electron volts, or it's WIMPs, when we're talking about 1 TeV, 10 TeV. Here the assumption is that they have masses close to the Planck scale, not quite. As I said, they would be stable, and you would see them. I mean, if I put up a detector, and this thing goes through your detector, you would get a beautiful track. And it's a track that would just go through, just straight through. Because these things are so heavy. So it's like when such a thing hits your detector or Earth, you know, atoms and so on, they're just like, it's like a torpedo moving through a mosquito swarm. So it will just go through. But it will leave this trace because it does interact with electromagnetically and strongly, possibly. And just to get an idea of if it were that this is dark matter, we can estimate, because I mean, how many of them can you have? Dark matter density is given by this number. And this means in order for the dark matter that we see, if it were made of protons, you would have 1 proton per cubic centimeter. If you scale this up to almost Planck scale, then you will have much fewer. You know, it would be like 1 super heavy gravitino in a cube of side length 20 kilometers or so. And then there's also a question of flux. Do they actually move? We have assumed that they move with matter in the galaxy, so they will have a velocity of, say, 100 kilometers per second or so. So it means that your detector would get hit only extremely rarely. And it could get worse, I mean, to the point that you can just not detect them if they cluster inside stars. This is some possibility that has been raised in connection with WIMPs, because people say maybe WIMPs are not, you know, just equally distributed, but maybe they get absorbed into stars and then they sit somewhere in the core. And then, you know, how can you see them? Maybe there's some effect in solar or stellar physics, but that will be hard to see. So, you know, in order to see these tracks, one idea would be to look for long ionized tracks in ultra stable matter, because if they're so rare, you know, the last one may have hit 1 million years ago. Well, we didn't dare to ask the English queen. She has a huge diamond, I'm told. Maybe that would be the appropriate thing to look at, but I think if you really did this experiment, you would have to sort of chemically attack the diamond, and then at the end of the experiment, nothing would be left of the queen's diamond. Anyway, there are people looking for, in fact, there are people trying to construct dark matter detectors that look for Planck mass like dark matter. So it's an experimental question. The second thing I want to propose is if these things really do get absorbed, and we don't see much of them, but they could, in principle, explain the ultra high energy cosmic ray events that have been observed over many years. Namely, if they cluster inside stars and the star collapses to a neutron star, then these things get close to enough to one another in order to possibly annihilate. Now, what do you get? I mean, if you collide two particles of 10 to the 17, 18 GeV, you get a huge energy, but because they're strongly interacting, you would see the same phenomenon as at LHC. You don't see few tracks, but there are hundreds and hundreds of particles coming out of each vertex in these strong interaction processes. And so what we did, we simply assumed that the mass of the particle gravitino is something like this. And then we took the formula that's, there's a formula for the multiplicity, empirical formula for the multiplicity of particles in such strong interaction collisions that gives you, that has been tested over the whole LHC range. So we simply take that formula, extrapolate it to Planck mass, and then you get a prediction that you should get about 1 million particles out of each collision. And then you multiply 10 to minus 6 with this, you get 10 to the 20 electron volts, which is more or less the kind of energy that we observe in these, or have been observed in these ultra high energy cosmic ray events. And in fact, this could even explain another feature, because what has been observed is that the high energy particles that come in are not just protons, they are heavy ions. And this is a complete puzzle, as far as, or at least, well, people have cooked up some kind of explanation, I guess, but it's something that's extremely hard to explain. And our hypothesis, it could be explained if you look at a neutron star. This is a paper that has some statement about the inner composition of a neutron star. So here see the neutron star, so the core inner crust. And if you look here, this is the last 60 meters below the surface, and this is the composition of the neutron star. So neutron star doesn't have neutrons on the surface, but it has heavy ions. So the idea is that somehow that these collision annihilation process, they can actually kick out these heavy ions from the neutron star. So that would be a possible explanation. Now, the last thing we've been thinking about has also come up in this sort of, I mean, you think, what are the uses, possible uses of super heavy gravitinos? Now, here's another one. People have observed these super massive black holes, like, you know, you saw the nice picture of 2 years ago. There was not the Milky Way galactic black hole, but some neighboring galaxy, and that has 1 billion solar masses. And with conventional physics, it's extremely hard to explain how they can come into being, because the usual accretion processes or stellar processes will not be able to get you to such large mass values. So we have hypothesized that these super heavy gravitinos, because they're stable, they're already around in the early radiation era of the universe, then they could cluster up and form bound states that subsequently collapse to little black holes. And for this, we have to make an assumption for the mass. You see, here's the mass. We assume the mass not quite to be the Planck mass, something we call the BPS mass. This is the mass where electrostatic repulsion equals the gravitational attraction. So if the mass is bigger than the gravitational attraction, will overwhelm the electrostatic repulsion that may exist between light-charged gravitinos. And then you can argue, and this is actually described in these two papers, that you can form a black hole as instability against collapse. In fact, there's even rigorous work of 50 years ago. Lévy-Leblanc has studied gravitationally bound systems and shown that it's unstable. And from this, you can now check what can happen. Now, the black holes, the seed black hole that you get will have very tiny mass. So normally you would say, well, if it's tiny mass, it will evaporate immediately by Hawking radiation. This is true in empty space, but there's a sort of competing process. In early radiation period, you have a very, very hot plasma. So the Hawking evaporation competes with the accretion absorption, and of course, this is a very complicated process because no one has done the Hawking calculation for this kind of time-dependent background. But roughly, the argument is as follows: as a rate, I mean, the equation for how the rate of the mass of the black hole changes. If it's just Hawking, it will be dominated by this term, which is for very small m, and then it will just evaporate away. But there's this competing term which describes the absorption in terms of the radiation density at time t, or you can also write it as a function of temperature. And this sort of feeds the black hole. This wants to make it evaporate. And so there's some competition. And you can sort of calculate a break-even point, well, actually quite easily. And then the claim is that this primordial black hole will start growing if initial mass is sufficiently large. And if you go back in time, very early on in the radiation period, it's extremely hot, and then this term is very big and will dominate. If the mass of the initial black hole, the C black hole, is smaller than this bound, then it will evaporate according to this argument. And we've checked, not just with this, but in this paper, we've sort of argued in terms of a solution of Einstein's equations, which is modeled on the so-called McVitie solution, which is, by the way, not well known, I think. But anyway, you can argue, you can actually calculate this, evolve it to until, the time when first inhomogeneities form or stars are born. And then you actually can get very, very close to the observed value. You should take these numbers, of course, with a grain of salt, but roughly it gives you what you want. And secondly, there's a sort of interesting further consequence of this, that there are competing explanations for this, of course, but other competing explanations will not have this kind of prediction because of this limit here that tells you that there must be a minimum mass for the black hole to form and to remain. You can sort of extrapolate it and then deduce from this there should also be a lower limit on the mass of galactic black holes. So it means that these black holes are in a different category from the ones that are formed by mergers of black holes like they observe at LIGO and Virgo. Well, it could be that, as I said, this number should be taken with a grain of salt. But I would like to emphasize that up to now, even though people have tried to look for these intermediate mass black holes, they haven't found any so far. So all we have is the, like 100 solar mass black holes from mergers. And then there are the galactic black holes. But in between, according to this scenario, there should be a gap. So this is, something that will be tested, because I'm sure there will be, keep looking for this. And then we will have to see what comes out of this. So here's my summary. So I've taken you the tour d'horizon a little bit. First of all, abstractly speaking, E10 and Ke10 are many reasons to believe that this is really a symmetry underlying a fundamental unification of physics, because they vastly generalize known duality symmetries. But, and this is another important point I wanted to make, this cannot be done within the framework of relativistic quantum field theory or space-time based physics. It does require a setting beyond known concepts of space and time, out of which then hopefully someday we can understand how physics emerges. But explaining how this emergence works, that remains an outstanding challenge. It's something we've been thinking about for the last 20 years and haven't really made much progress, if any. So it seems like here something, some radical, some quantum leap is required. And this is, you see, this is where it's somehow the mathematics and the physics link up, because on the one hand, we want to understand what is E10, that's a mathematical challenge. On the other hand, you want to understand what are the fundamental degrees of M theory. That's difficult. equally difficult physical question, but somehow it could be that the two questions are linked in a very subtle way, and we cannot solve one without solving the other. Then I've shown you links between K10 and standard model fermions. I've emphasized that E10 and K10 may supersede supersymmetry. Now, supersymmetry has been dominant paradigm for the last 40 years. There were really great hopes connected with it, such that in the early 2000s, even experimentalists had been become completely convinced that they simply need to switch on LHC and out these particles would just pop out like this. So of course the disappointment was accordingly huge. I mean, I think people are still disappointed to the point that they will not give up on the idea, and maybe there's supersymmetry at 100 TeV or so. This is something that we don't know. But to be quite honest, I think my interpretation is that a good part of the community has been barking up the wrong tree, because this seems to indicate that maybe supersymmetry is not as fundamental as we think it is. And it's also clear that in a context where space and time are emergent, that you don't know what the role of supersymmetry is, because that hinges on space and time. Q with Q gives a translation in space-time. So what becomes of this, or whether there's any relevance at all in a context where there's no space-time to start with, remains open. My guess would be it's just not there, but instead you have to look for something like this. As I said, there's a definite prediction. It just fits with a standard model spectrum that we see, plus 8 gravitinos. And here I've tried to argue that there may be possibly interesting implications also for some astrophysical questions of current interests. So this is why I entitled my talk towards searching for new paradigm. There was like 2 or 3 weeks ago, there was in this series of GGI seminars, there was also a talk by Can Giudice, who also thinks that we should be looking for a new paradigm, but his paradigm is more like multiverse, and so it's quite different from what I showed you here. So thank you very much for your attention.
Well, thank you very much for this beautiful talk that advocates for K of E10 and E10. But I think that the audience was already convinced to a large extent. But do we have questions? Yes, there is a question in the chat from Marius. Maybe, can you see it?
How do I see it?
On your screen.
No, I can, it's not written. I can say it.
Yeah, say it. Why don't you say it?
I can ask the question.
Okay.
Hello, Hermann.
Hello, Marius.
Ask your question.
So my question actually is a little bit on the border of what you said regarding the black holes. You mentioned towards the end of your talk that somehow you find something which is compatible with the present observations, namely that there is a gap in the spectrum of masses of black holes. So my question is the following: what do our astrophysicist colleagues find as an explanation for this gap at the moment?
Well, I'm not even sure whether they're looking for an explanation, because I think many of them stay convinced that there actually should be such black holes. And this would be somewhat against my proposal. But there is actually a paper that was referred to in, let me see, the paper is referred to in this publication. There's a team of people that has looked at something that looked like an intermediate mass black hole somewhere. It seems to be an object that is of 10,000 solar masses. And then they looked at it very closely, and then it's very confused because they say that this is not really a black hole. It's more like an assembly of, many little black holes in a region that's, comparable to the size of the solar system. But anyway, they cannot identify this object as a single object from which this gravity comes, but it looks more like the mass is scattered, but there's not a single black hole. So they do, I think they are actually open to this possibility, but I think with many of them, the expectation is that sooner or later, we will also see black holes of 10,000 solar masses. So, that's an observational question.
Thanks.
In fact, what I've heard about, there's also now this idea being propagated that dark matter could all reside in black holes. And then, our gravitinos, which I tried to sell you before, they could still be there, but they're just condensed into black holes. And I think that scenario also requires that you have a continuous spectrum of black hole masses. So it's in some sense all up in the air, but I wanted, maybe I should emphasize, because particle physics gets kind of depressed about, we've LHC, but the next accelerator will, not sure whether it will ever come, but there's lots of things in astrophysics that are, open questions, like these ultra high energy cosmic rays, the black holes that you see, the huge black holes, and maybe there are even other things, so this is one avenue I'm trying to pursue with Christoph. We try to think of, maybe there's even a way to see gravitinos in the CMB. It sounds crazy, but I mean, there are many opportunities here. Let me put it this way.
Yes, to continue on what you just said, one has the feeling that you have super heavy gravitino which have strong interactions. You should see some other remnant of that from the CMB. I don't know, because they should be more strongly coupled and interacting at early times. You tell us that now they can cross the Earth without interacting, but I guess at early times maybe other phenomena could be.
Yes, that's possible.
Could appear. I don't know.
But I'm pretty sure there will be very tiny effects. I mean, this is. I don't know. I mean, certainly we want to think in this direction, and we'll have to see whether this is viable.
Okay, so there is a question from Guillaume.
Hi, Hermann. Yeah, coming back to the black hole. Hi. I'm slightly confused by what you said, because I thought that the expectation from theory actually in astrophysics was that there should be a gap, but actually there should be a bigger gap, in the sense that I thought they had a very hard time explaining for very large mass stellar black hole, like already 100 solar mass was already not explained, because from a collapse of a big star, you don't expect such a thing, so they are completely different from. So
no, I think even explaining 100 solar masses just from supernova collapse is difficult, or maybe even impossible. But what does happen, and this is what they've actually seen, if you collide these black holes, then you can easily increase their masses to, I think the biggest they've seen is like in these collisions, it's about 150 or so solar masses. And they could even maybe bigger even.
Yeah, but I thought that was mainly based on experiment. They see them, so they know they are there, but they did not really expect them from theory, so they have to work more.
No, of course.
So you would expect a gap in that sense, because there is not supposed to be.
There was, there was a big surprise when they first saw them, because they hadn't expected. Already the very first one, I think, they were surprised about the mass. But now, once one understands the abundances and how often they can collide, and there's a long time in which they can collide. So you can sort of build models and sort of calculate, although I haven't done it, but in principle it seems feasible to sort of, on this basis, estimate how many times black holes, solar generated, stellar-like generated objects could have merged, and how big in mass then you would be able to go. But it seems to me that maybe a few hundred, but it will probably be hard. They have first to form, and then they have to collide, and they have to collide again and again and again. And by that time, probably 15 billion years are up, and that's what might set an upper bound.
Maybe another question on experiments, that you mentioned the fact that you could be falsified by experiment of new particles, but also if they would prove in some reasonable amount of time that neutrinos were actually Majorana mass and not Dirac mass, would it also kill the model?
No, I think that's not a problem, because I mean, this is of course something to do with the dynamics, on which I cannot really say anything. But
no, it's not only dynamics, right? You don't have to double the. You don't
no, but this scheme does contain right-handed neutrinos.
Yeah, so if they are Majoranas, there is no need for right-handed.
No, but once you have the right-handed neutrinos, you can write a Majorana mass, Majorana type interaction, and generate Majorana. I mean, the usual seesaw mechanism, but that I don't see any reason why it cannot work in this scheme.
Yeah, but for Majorana, you use the right-handed. I mean, it's the own particle. Which is its antiparticle, so you don't need extra particles. So you would have more particles than the standard model, then, no?
No. If you have, I mean, in right and left-handed is like two Majorana masses, so the counting is the same, but whether it's its own antiparticle or not, there's something to do with how you arrange the self-interactions between these neutrinos. I would have to think about it, but in the past we have thought about this, and I wouldn't see any immediate problem with this.
Okay, thank you. Any other question? Yeah, perhaps I have one last, general question about your comment that maybe supersymmetry is not needed, but a good thing of supersymmetry is that if you have bosons, you have also fermions. So I guess in principle, you could have a consistent E10 model with only bosons, without the super heavy gravitinos. Or why would you need them?
Well, that's not so clear, because I think, one thing I've been thinking about without getting anywhere, admittedly not getting anywhere, is that you may also have some kind of bosonization with the fermions, because once you're one-dimensional, then you can bosonize. So, I mean, the very distinction between a boson and the fermion hinges on space-time, because it means that when you rotate by 2 pi in space, you get a factor of -1. But what's the analog of that statement in the context when there is no space? And then, so it all becomes very blurred. And, in some sense, this very notion of what is a space-time fermion and what is a space-time boson may also be emergent in some sense.
Okay. Well, thank you very much. If there is no other question, let's thank Hermann again for this beautiful talk.
Well, thank you very much for listening, and
thank you. And so
I wish you all well, and please stay healthy.
And I hope to see you in Paris at some point.
Absolutely, absolutely.
Well,
we're very keen on moving out of lockdown in some sense.
Okay, and there are optimistic signs, or it is signs for optimism at least.
Yes, let's hope that they will prevail and that there's not a fourth wave in autumn, because that means that again we wouldn't be able to travel.
Okay, well, thank you, and bye-bye.
Bye-bye. Bye-bye.